So today's lecture is over section 2.5 in your textbook, piecewise defined functions. And a piecewise function has multiple formulas in evaluating the function, and each formula applies to a different part of the domain. So in example 1 in your notes, we have f of x is equal to, the formula is 3x plus 1 if x is less than or equal to -1, and f of x is equal to x squared minus 1 if x is greater than 0. Okay? And you notice that the domain of the function is broken up into disjoint intervals. There's no overlap between this interval and this interval on the domain. Okay? So if x is less than or equal to -1, right, this is the formula for a straight line. And if x is greater than 0, this is the formula for a parabola. Okay? And so in part A and B, you're asked to evaluate the formula at different values of x. So we're going to do that in this part right here. So the f evaluated x equals -1. Well, -1, right, is less than or equal to -1. So we use the first formula in evaluating the function f at x equals -1. And we put in -1 for x. We have 3 times -1 plus 1, which is equal to -2. So I've already have a correction. It's equal to -2. And so the point -1, -2 is on the graph of this piecewise function. Okay? To evaluate the function at x equals -2, okay? -2 is less than or equal to -1, so we use the first formula to evaluate the function. F of -2 is equal to 3 times -2 plus 1, which is -5. And so the point -2, -5 is on the graph of the function. To evaluate the function at x equals 2, f of 2, well, 2 is greater than 0, so we use the second formula evaluating the function at x equals 2, and we put in 2 for x. We have f of 2 is equal to 2 squared minus 1, which is 3, and so the point 2, 3 is on the graph. Okay? Now, the second formula only applies for x strictly greater than 0, so on the graph of this function, there's going to be a hole in the graph at x equals 0. And to find the y-coordinate of where that open hole is, we just put 0 in for x in the second rule. And so we have 0 squared minus 1 is equal to -1. And so there's going to be an open hole in this graph at 0, -1. Okay? So part A in this problem is evaluate the function at x equals -1. We found that to be -2. Part B, evaluate this function at x equals 2. We found that to be equal to 3. Okay? And we'll do C and D, the domain and range, after we graph the function. So let's now graph the function. And so for x less than or equal to -1, we know the point -1, -2 is on the graph. So I've provided you with a grid. I've hand drawn it on the board here. So here's -1 on the x-axis. Here's -2 on the y-axis. So there's the point -1, -2 in the coordinate plane. And then the point -2, -5 is on the graph. So here's x equals -2. Here's y equals -5. And the graph of the function for x less than or equal to -1 is a half line. So it just goes starting here at -1, -2. It goes through that point at -2, 5, and down forever. Okay? Now for x, the graph for x greater than 0, we know there's an open hole at 0, -1. So here's the origin. So we go down 1 unit to y equals minus 1. And so at y equals minus 1 is the open hole. And then we also know at x equals 2, right? The point 2,3 is on the graph. So here's x equals 2, here's y equals 3. And we know that for x greater than 0, right, the graph is part of a parabola. And so it actually also, the graph crosses the x-axis at x equals 1. So when we play connect the dots, we see that the graph looks something like that for x greater than 0. Okay? And you can see it's not a continuous function, because as I trace out the graph with my finger, when I get to this closed circle, I gotta take my finger off the board and move it over here to the open circle. Right? So it's not a continuous function, it's discontinuous. Okay? What's the domain in interval notation? Well, you're given the domain over here in the piecewise function. The domain is x less than or equal to -1, union x greater than 0. So how do you write x less than or equal to -1? Minus infinity to -1 bracket, because we're including -1. And then how do you write x strictly greater than 0? Parentheses, 0, infinity. So that's the domain for this function. What's the range? We know the range is all the y values, right? All the y coordinates in the graph. So here on the left, the half line goes down forever, so there's no minimum y value. And then it comes, the maximum y value on this part of the graph is -2. So for this part of the graph, the range is minus infinity to -2. And then we got to add to that the range from this part of the graph. And strictly speaking, right, -1 is not in range because it's an open circle, but the range, right, there's no maximum y value, right? So it would go to infinity, the range would go to infinity, but the range, right, begins at -1 and goes to infinity, but we're not including -1 because of the open circle. So we have parentheses, -1, infinity, parentheses for the range. Okay? And that's parts C and D in this question. All right, so in example 2, part A, we have to graph the function f of x is equal to the absolute value of x minus 2 divided by x minus 2. So let's first review what absolute value of x minus 2 means. The absolute value of x minus 2 is just equal to itself, x minus 2, if x minus 2 is greater than or equal to 0. And it's equal to the negative of x minus 2 if x minus 2 is less than 0, right? This is exam 1 material. Well, now if we divide both sides by x minus 2, we have the absolute value of x minus 2 divided by x minus 2 is equal to 1, right? X minus 2 divided by x minus 2 is equal to 1 if x minus 2 is greater than or equal to 0, and it's equal to -1, right? Because the negative of x minus 2 divided by x minus 2 is equal to -1. This is equal to -1 if x minus 2 is less than 0. Okay? Now, x minus 2 greater than or equal to 0 is the same as x greater than or equal to 2. And x minus 2 less than 0 is the same as x less than 2, right? All I did was add 2 to both sides of these inequalities. Okay? And so now we can graph this function, f of x equals the absolute value of x minus 2 over x minus 2. Okay? For x greater than or equal to 2, right, the function is equal to 1. So that's just a half line starting at x equals 2, okay? A half line, and so the point 2, 1, right? This is the y coordinate, right? So for every value of x greater than or equal to 2, the y coordinate is 1. And so the graph for x greater than or equal to 2 is a half line starting at x equals 2, right? And y equals 1. This is the point 2, 1. So we just have a half line, a horizontal half line going to the right. For x less than 2, all the y coordinates are negative 1. So here is x equals 2. Here's y equals negative 1. And so we have an open circle at x equals, at the point 2, 2 minus 1 in the coordinate plane, right? Because this is strictly x less than 2. And then we have the half line going to the left from the point 2 minus 1. That's an open circle there, though, okay? And so that's what the graph looks like for this function, okay? All right, what's the domain? Well, when you join x greater than or equal to 2 and x less than 2 together with the union symbol, you get all real numbers. So the domain is all real numbers. Okay? This function is defined for every value of x from minus infinity to plus infinity. Okay? But you notice that there are only two y values in this function, minus 1 and plus 1. And so that's the range. Right? All the y coordinates in the graph of this function are either minus 1 or plus 1. And so the range is actually a set of two numbers, minus 1 and 1, right? So here we're using braces. We have a set with two numbers in it. That is the range. All right, in example 2, part B, we're graphing the piecewise function f of x is equal to negative 3 if x is strictly less than negative 3. F of x is equal to x if x is greater than or equal to negative 3 and less than or equal to plus 3. And then f of x is equal to 2 if x is strictly greater than 3. And you might notice that the domain for this function is all real numbers, because when you join all three of these intervals with the union symbol, you get all the real numbers from minus infinity to plus infinity. Okay. All right, so the easiest part to graph first is the middle part of this function. F of x equals x, right, for x greater than or equal to negative 3 and x less than or equal to plus 3. Right? There are no open circles. So f of minus 3 is equal to negative 3. So the point minus 3 is on the graph. F of 0 is equal to 0, so the point 0, 0 is on the graph. And f of 3 is equal to 3, so the point 3, 3 is on the graph. So here's the point minus 3, minus 3. You've been provided with a grid, and then the line goes through the origin up to the point 3, 3. Here's the point minus 3, minus 3. Here's the point 3, 3. And then the graph from x equals minus 3 to plus 3 is actually a line segment between these 2 points and goes through the origin. Okay? So that's what the graph looks like from x equals minus 3 up to x equals plus 3. Okay? Now for x less than negative 3, f of x is just equal to negative 3. All the y coordinates are equal to negative 3. So for x less than negative 3, we just have a half line going to the left, a horizontal half line going to the left, right? All the y coordinates on this half line are equal to minus 3. For x greater than 3, f of x is equal to 2. Well, here's, right, all the y coordinates are equal to plus 2. So here's x equals 3, and all the y coordinates, right, for x greater than 3 are equal to 2. So we just have a half line going to the right, okay, a horizontal half line going to the right of the open circle at 3, 2, right? There's an open circle at x equals at the point 3, 2, because at x equals 3, the value of the function is plus 3, not plus 2. Okay? And so that's what the graph of this function looks like. Okay. All right. So what's the domain? Domain is all real numbers. When you join all three of these intervals together with the union symbol, you get all the real numbers from minus infinity to plus infinity. And you can see that in our graph, right? It's continuous from here, right? So it goes to the left forever, right? It comes here and up to here, it's continuous, right? Then at x equals 3, it jumps down here to the open circle, and it's continuous. So for every value of x, there is a point on the graph with that x coordinate, okay? Now the range, the y values, the minimum y value is minus 3. Right? And in this part of the graph that is continuous, the maximum y value is plus 3. And this part of the graph has a y value, right? The y coordinates are plus 2, and plus 2 is between minus 3 and plus 3. So the range for this function, right, is minus 3 to plus 3. Y is greater than or equal to negative 3, and less than or equal to plus 3. All right, so if you flip over to page 2 of your notes, over at the top of page 2, we're going to graph the absolute value function. F of x equals the absolute value of x. And the absolute value of x, as you know, is equal to x if x is greater than or equal to 0. And it's equal to negative x if x is less than 0. Okay. So there are many ways to graph this function. I'm just going to go back to maybe your old high school days of learning how to graph a function. Right? You make a table. In the first column, you put some values of x. In the second column, you calculate the corresponding values of y. And then you form the ordered pairs. Then you plot the ordered pairs, right? The points in the coordinate plane. And then you connect the dots. So I use minus 2, 0, and 2 for my values of x. So when x is equal to minus 2, y is equal to the absolute value of minus 2, which is 2. So the point minus 2, 2 is on the graph. When x is equal to 0, y is equal to the absolute value of 0, which is 0. So the origin is a point on the graph. And when x is equal to 2, y is equal to the absolute value of 2, which is 2. So the point 2, 2 is on the graph. So now we plot these 3 points in the coordinate plane, and then we connect the dots. And when we do that, we see that the graph of the absolute value function is V-shaped. Okay? And it's also symmetric to the y-axis, right? The right half is a mirror image of the left half. The left half is a mirror image of the right half. Okay? So the absolute graph of the absolute value function is V-shaped. Now, what's the domain? The domain is all real numbers, right? This on the left, the graph goes to the left forever. On the right, it goes to the right forever. For every value of x, there is a point on the graph with that x coordinate. So the domain minus infinity to infinity. The range, which is the y-coordinates, the minimum y-coordinate is 0, right? Because the origin is the lowest point on the graph. There's no maximum y-coordinate, and so the range is from 0 to infinity, including 0. Right? Y greater than or equal to 0 is the range for this function. All right, so in example 3, page 2 of your notes, part A, we are going to graph the function f of x equals the absolute value of x plus 3 minus 2. And you might recognize that that is just a transformation on the graph of the absolute value function. F of x equals absolute value of x, right? We just did that one. And so when we replace x with x plus 3, that shifts this graph to the left 3 units. And then when we subtract 2, it then shifts this graph down 2 units. So every point on this graph will get shifted to the left 3 units and down 2 units. So this vertex at the origin, right, is now at the point minus 3, minus 2. And then we have the V-shaped graph. And so it crosses the x-axis at minus 1 and crosses the y-axis at minus 5. Okay? So this point here, 2, 2, gets moved to the left 3 units and down 2. And this point minus 2, 2 gets moved to the left 3 units and down 2. And so when we graph this function, we see that it crosses the x-axis at minus 5 and minus 1, and those are the x-intercepts for this graph. All right. In part C, example 3, part C, we are graphing the equation y equals 3 minus the absolute value of x plus 1. Well, that equation is just a transformation on the absolute value function. To go from the absolute value function to this equation, we replace x with x plus 1, which has the effect of shifting the graph to the left 1 unit. And then when we take the negative or multiply the right-hand side by minus 1, that will then flip the graph over the x-axis. So the vertex goes from x equals 0 to x equals minus 1. And then when we flip the graph over the x-axis, the vertex is still at x equals minus 1. And then we shift the graph up 3 units. And so the vertex goes from x equals minus 1 up to x equals minus 1, y equals 3, to the point minus 1, 3. And so I graphed the equation over here, right? We started with the vertex here at the origin, and it got shifted to the left 1 unit to x equals minus 1. Then we flipped the graph over the x-axis, and then we shifted the vertex up 3 units. So this is the point minus 1, 3. Okay? And then the graph is V-shaped going downwards. And it crosses the x-axis at minus 4, crosses the y-axis at minus 2, and crosses the x-axis at plus 2. And you can put in minus 4 in for x up here. Minus 4 plus 1 is negative 3. Absolute value negative 3 is 3. 3 minus 3 is 0. Right? So that is the x-intercept, one of the x-intercepts. The same with x equals 2. Putting 2 in for x, 2 plus 1 is 3. Absolute value 3 is 3. 3 minus 3 is 0. So x equals 2 is the other x-intercept. That's what the graph looks like. All right, so now looking at example 3, part B, we're going to graph the function f of x is equal to the absolute value of the negative of x minus 2 squared plus 4. Now, if you look just what's inside the absolute value bars, you'll notice that that's a transformation on the function, on the x squared function, right? The squaring function, y equals x squared. So here I have the graph of f of x equals x squared. You know it's a parabola that goes through the origin, right? It's U-shaped, opens up, and passes through the points 1, 1, 2, 4, minus 1, 1, minus 2, 4. Now, if we just look at what's inside the absolute value bars, look at the graph of the equation y equals a negative or minus x minus 2 squared plus 4. This equation is a transformation on the squaring function. F of x equals x squared. We take the graph of the parabola, right? So the graph of this equation is the graph of this parabola shifted to the right 2 units, then reflected over the x-axis, flipped over the x-axis, and then shifted up 4 units. So the vertex here at the origin gets shifted to the right 2 units to x equals 2. And then when they flip it over the x-axis, the vertex stays at x equals 2, and then it gets shifted up 4 units to the point 2, 4. So here's the vertex for this equation, for the graph of this equation at the point 2, 4. And you know it opens down, right, because of reflection across the x-axis. And then every point, right, so we got to take every point here and shift it to the right 2 units, flip them over the x-axis, and then shift them up 4 units. And we see that the parabola for this equation crosses the x-axis at x equals 4 and at x equals 0. Right? X equals 0 and x equals 4 are the x-intercepts for this graph. But now what we want to graph is the absolute value of minus x minus 2 squared plus 4. And absolute value takes any function value that is negative and makes it positive. Okay? The absolute value of anything is positive. So these parts of the graph that are below the x-axis, right, they have negative function values, negative y values. So when we take the absolute value, the y coordinates for these parts of the graph that's below the x-axis, they change sign. They become positive, and so this part of the graph gets flipped over the x-axis and goes up and to the left, and this part of the graph that's below the x-axis gets flipped up and goes up and to the right, and that's what we have here. Okay, the part that was going down below the x-axis is now going up, and over here the part that was going down gets flipped over the x-axis and is now going up, and that's because of that absolute value. It made those parts of the function that were negative positive. The y coordinates went from negative to positive. All right, so now we're going to graph in D, example 3, part D of page 2 of your notes. We're going to graph the equation y equals the absolute value of x cubed minus 2. And you can see what's inside the absolute value bars is a transformation on the cubing function, x cubed. So we've graphed this before. Right, here's a graph of f of x equals x cubed. It snakes through the origin, right? So the origin 0, 0 is on the graph. The point 1, 1 is on the graph. The point minus 1, minus 1 is on the graph, and the cube root of 2, comma 2 is on the graph, and that's an important point for this problem. So what's inside the absolute value bars is a transformation on the cubing function, right? We're just shifting it down 2 units. When we subtract 2 from the right-hand side, right, the graph of x cubed minus 2 is the graph of x cubed just shifted down 2 units. And so instead of crossing the y-axis at the origin, it now crosses the y-axis at y equals minus 2, right? So 0 minus 2 is the y-intercept. and the graph goes through the point. So all the points on this graph get shifted down 2 units. And so it goes through the point 1, -1, and -1, -3. And the x-intercept for this graph is x equals the cube root of 2. Okay? Now we're taking the absolute value of the right-hand side. And when we take the absolute value of the right-hand side, everything, the part of the graph that's above the x-axis stays the same. The part that's below the x-axis gets flipped over to the x-axis because all the y-coordinates go from being negative to being positive. Right? We just change the sign of all the y-coordinates from negative to positive to get the graph of the absolute value x cubed minus 2. And so when we do that, when we flip the part below the x-axis above the x-axis, then now we see that the point 1 -1 right here, when we change the y-coordinate from -1 to +1, we see now the graph goes through the point 1, 1. The y-intercept, y equals -2. The y-intercept is now y equals +2. And so it crosses the y-axis at +2 now. Right? The point 0,2 is on the graph. The point -1, -3, the y-coordinate, we change from -3 to +3. And now we see the point -1, +3 is on the graph. The x-intercept stays the same. It's x equals the cube root of 2. And so the x-intercept is cube root of 2, 0, written as an ordered pair. All right, last graph. So example 3, part E, we're going to graph y equals the absolute value of the square root of x plus 2 minus 1. And so if you look at what's inside the absolute value bars here closely, this is the transformation on the square root function. So here I have the graph of y equals the square root of x. We've graphed it before. Right, the domain is x greater than or equal to 0. It starts here at the origin, passes through the point 1, 1, passes through the point 4, 2. Now, the graph of the equation square root of x plus 2 minus 1 is a transformation on the square root function. Right, the graph of this equation is the graph of the square root function shifted to the left 2 units and down 1 unit. So every point on this graph gets shifted to the left 2 units and down 1 unit. So here where it starts at the origin, it now starts at -2, -1, crosses the x-axis at x equals -1, and the point 2, 1 is on the graph. Now to find the graph of y equals the absolute value of square root of x plus 2 minus 1, everything that is above the x-axis stays the same. So everything to the right of x equals -1 is above the x-axis. So that stays the same. What changes is what's below the x-axis. This part here that's below the x-axis, the y-coordinates get changed from negative to positive. So this point -2, -1, the y-coordinate gets changed to +1, and we see the point -2, 1 is on the graph of this equation. And this is what the graph looks like for x between -2 and -1. So this is what the graph of the absolute value square root of x plus 2 minus 1.